All right, good morning, everyone. We still got a minute to 2 minutes, so we're just gonna wait a minute or two to get everybody into the room, and then we'll be starting our seventh session of the Geo Hackathon. Um, thank you all for being here. All right. One more minute, and we'll start. All right, hello everyone. Welcome to session number 7 of the Geo Hackathon 2024. Really excited to be here today as the moderator. This topic is super awesome, and we get some super awesome presenters. Essentially, what we're going to talk today about is heat flow quantification. So, if you think of reservoir engineering in regular oil and gas, you're looking at flow of gas and oil and fluid dynamics, and now we're looking at heat. How are we harnessing this heat? How is the heat moving from into the rock? How is the heat moving into the rock, and then how do we get it to surface? How do we maximize that? So I'd like to introduce our speakers without further ado. So we have one of our speakers today here is Yamal Askoul, who is the global subject matter expert in reservoir engineering with Gaffney Klein Baker Hughes. He is an experienced senior reservoir engineer with more than 20 years working in the oil and gas, and he has gathered great skills in dynamic simulation, reservoir characterization, dynamic reservoir engineering, lower completion modeling, so ICDs and AICDs, unconventional reservoir, improved and enhanced oil recovery, including CCS, CCUS, UGS, and geothermal. Also, he has experience in geomodeling, field development plans, implementing uncertainty analysis, flooding schemes, and water management. He had the opportunity to work on projects with different types of reservoir fluids from heavy to light oil, dry gas, wet gas, and condensate gas. Likewise, he has experience in clastic reservoirs from consolidated to unconsolidated bedrock and carbonate reservoirs. To conclude, Yamal is knowledgeable in oil and gas field optimization, forecast production, reserve estimation by following PRMS, energy transition evaluation project considering SRMS, field enhancement, and rejuvenation production, decline curve analysis, well testing analysis, so build up and drop down, and well testing program design, and background on oil and gas economic evaluation. I am more than certain that we have the best people here today. Our second speaker today, the main speaker that will be running the talk, is Elkin Rodolfo Santafé Rangel. I hope I said that correctly. The senior reservoir engineer with Gaffney Klein at Baker Hughes. So he joined the European, North Sea, Caspian, and Sub-Saharan Africa work team in 2023, quite recently as a reservoir engineer and discipline advisor. His role involves the application of numerical reservoir simulation, and classical reservoir engineering on critical projects related to CO2 utilization and storage in depleted fields and aquifers, geothermal energy assessment, decommissioning analysis, underground gas storage, and other net zero and oil and gas initiatives. Mr. Santafé started his career in 2005 in Ecopetrol as an external consultant for the Colombian Institute of Petroleum, moving next to Schlumberger as a reservoir engineer for the Information Solutions segment, and finally a senior reservoir simulation engineer for Best Energy in Ecuador. This career path gave him practical experience through projects in basins such as the Llanos foothills in Colombia, based in North Ecuador, and the Gulf of Mexico. He has also cultivated his passion for knowledge transfer and interaction with academia, being an international instructor for the Educational Services segment, next at Schlumberger, and adjunct professor at the School of Petroleum Engineering at the Industrial University of Santander. Mr. Santafé has a degree in petroleum engineering and a Master of Science in Systems Engineering and Computer Science, both from the Industrial University of Santander in Colombia. I would just like to say to all the participants that are here to know that the geothermal world has got a lot of opportunities. As you can see from our esteemed speakers today, your career in subsurface can be anything, whatever drives your passion. And this is part of what we're trying to do here with the hackathon. So we'll go ahead and do here. I'll stop sharing. I'll pass it on to you, Elkin, if you don't mind sharing your slides. We are recording this session as always. This session will be uploaded on Discord. We will also be sending the slide packs. We're going to upload the previous slide packs as well on the Discord channel, so you can access them and look over them. Perfect. We can see your screen. If you don't mind unmuting yourself, and enjoy the session. Any questions, put them in the chat box and we will be moderating those at the end of the talk.
Okay. Hello, everyone. Can you see my screen now?
Yes.
Okay, perfect. So thank you so much for the opportunity to share with all of you today this technical session related to the geothermal energy heat flow quantifications. And we are going to share a piece of the work that we have been developing in terms of the analysis of the geothermal energy resource assessment that basically we have been developing here at Baker Hughes. And basically, we will like to cover everything, but we just have a limited time. So we are going to do as best as possible the effort to cover the basic ideas that lead you to understand what is the basis behind of this problem in terms of the heat flow quantification and temperature quantification. So let's start with the agenda for today. So basically, we are going to cover in the three main topics. We are going to review the heat transfer processes in the well, but by using a general framework and definitions. We are going to, after that, we are going to cover the temperature modeling in the well in terms of the modeling process. And finally, we are going to talk about the overview of geothermal reservoirs, trying to abording some elements related to how we, in the practice, we usually try to implement the systems by using, for example, numerical reservoir simulation and by taking into account the system cycle. So let's start with the first topic, the heat transfer process in the well. So the heat is a form of energy, basically. Specifically, it is a thermal heat energy that is transmitted from one body to another if they have different temperatures. And as a general rule of thermodynamics, the heat always flows from the body with the highest temperature to the one with the lowest temperature, basically. So this occurs until thermal equilibrium is reached. Yeah, that's it. Both substance or objects have the same temperature, basically. This heat transfer can occur through different processes or mechanisms that are precisely a process that we are going to review more in depth. So these processes are basically conduction, convection, and radiation. So let's try to describe in general lines what each of these mechanisms is about. So conduction is the transfer of heat by direct contact between the molecules of a body of substance. What happens in this case is that the molecules impact each other, uh, as we can see here. Yeah, and in that way, they transferring heat between them. So this process can occur in solids, in liquids, and gases. And the heat can be conducted within the same substance or body, but if we have two individual bodies at different temperatures that are in contact, the heat conduction will also occur from one with the highest temperature to the one with the lowest temperature, basically. So now the speed at which this heat transfer occurs depends of a property well known as a thermal conductivity. So let's talk about that property. Um, this thermal conductivity basically determines the ability of a material or substance to conduct heat. Here in this table, we can see values with different materials. They correspond to thermal conductivity. And in particular, we can see that the wood has a relatively low thermal conductivity. On the other hand, the silver has a high thermal conductivity. What this implies is that if we expose the same amount of wood and silver to the same heat source, basically wood will conduct heat more slowly. So therefore we say that it is a thermal insulator, while on the other hand, silver will do so much more quickly, which is why we say that this is a good thermal conductor. If we continue looking at the table, we can see that air also has a low thermal conductivity. So let's suppose that we have an oven at 200 degrees Celsius. In this case, both the grill and the air inside the oven are both at 200 degrees Celsius. However, if we put a hand into the oven without touching the grill, we will feel that the air is hot, but it doesn't not burn us, even though it is 200 degrees Celsius. And this is again because the air is a poor conductor, basically. So of heat is a poor conductor of heat. So the heat doesn't basically pass so easily to our hand, and we do not burn ourselves immediately. So now, if in the same case, sorry, in the same case, if we try to touch the grill, which is at the same 200 degrees Celsius, we will burn ourselves since the metal is a good conductor. So basically, the heat will be conducted more quickly. That is the idea behind this example. And this is a good view or in a typical situation of the life about how the thermal conductivity is working depending of the situation and material. So in addition, we can say that conduction doesn't only depend of thermal conductivity. So it is the most relevant property, but it is not the only dependency in terms of the relationships that exists to this variable. So the speed at which the heat is conducted may also depend in part of the temperature difference between the bodies and the exposed area, as this relation is basically exposing. Mm, it what we can say in addition is that it has been experimentally demonstrated that the rate of the heat conduction in a plate, for example, this plate, yeah, depends on the temperature or the difference of temperature between each side and the exposed area. So, but is inversely proportional to the thickness of that same plate. So we can express this relationship in terms of deltas, as we can see here, and then take those deltas to the limit to convert them into continuous differentials. So in that way, we can write the same expression that we have here in terms of a differential, simple differential equation. And this equation is what we know as a Fourier law. So moving now to an other heat transfer mechanism. So we are going to talk about convection. So convection is the transfer of heat by the movement of mass. That is, it occurs in fluids, and this implies that we will only find it in liquids and gases, right? So we can divide this convection, because it's a complex mechanism. We can divide it into mechanisms: natural convection or free convection, and forced convection. Mm, let's talk about free convection first. So uh, the free convection or natural convection occurs when the movement of the fluid is caused by the density difference, which in turn are products of temperature difference, basically. So, for example, let's suppose that we heat a container that has a fluid inside. Let's talk that we have inside just air. So what will happen here initially is that the heat is transmitted by conduction to the air that is at the bottom. And as we know, a change in temperature, yeah, in a fluid generates a change in density, basically. So in this case, the air, when heated, becomes less dense, and since it is less dense and tends to rise. So we will have a movement uh, in this direction up, and the cold air basically will go down. Mm, in this situation, to replace the hot air that is rising, the cool air at the top is forced, yeah, so that air will descend, and we know all of this mechanism as a free convection. So mm, on the environmental level, let's talk about our planet as a system. Yeah, this type of convection normally occurs in fluids when the heat is supplied from below, as happens, for example, in the atmosphere. So that is why we can say that free convection is one of the phenomena that largely determines atmospheric circulation, both on a global and local scale. Those also determine the meteorological phenomena that we can see daily. Mm, now we have the forced convection. The force of convection occurs basically when the movement of a fluid is caused by external factors other than the local behavior of the fluid, basically. A clear example of this is when we turn on a fan to force the flow of the air over the hot surface. In this case, the air that is forced to flow over the hot surface acquires heat through conduction. But by definition, this is called convection, since we are talking about the mass movement that transfer heat from one area to another area. So we are moving cool air or air that is cold in this area to air that is now hot at this level or on this part of the system. In summary, uh, we can say that convection is a complex mechanism, as I say before. It represents the combination of two ways of transferring heat, and we can give a mathematical image through the Newton's law of heating and cooling. That is the mathematical model that describes this phenomenon. So this model is composed by the rate of convection, heat transfer, expressed normally in units as a watts per square meters. Uh, and we say that this variable is proportional to the difference between the initial temperature of the material and the final temperature of the material throughout a proportion constant that we are going to call H. So we are going more in deep about what is the meaning, physical meaning of this H in a further slide. So for now, we are managed that like a proportion constant. So we should also mention that the rawness and the shape of the material being heating has an impact in this process. And the value can change by doing the heating or cooling process of an object more quickly. This value, when we change the value of H. In the particular case of forced convection, which is perhaps one of the most present mechanisms, in addition to the fluid properties and rawness of the solid surface that is in contact with the fluid, the type of the fluid I'm talking about if is laminar or turbulent has an impact too. For example, in the diagram that we can see here, yeah, if we assume that the velocity of the fluid is zero at the wall, as a result, the heat transfer from the soil surface to the fluid, the layer that we have here, adjacent to that surface is by pure conduction, but just in this point, really, really close to the wall, since the fluid is motionless. So the convection heat transfer coefficient in general varies along the flow direction, right? Or in terms of the radial and in terms of the direction in which the fluid is moving. So in many cases, we do what we do is to use an average convection heat transfer coefficient. Mm, Now, let's talk a little bit about the last heat transfer mechanism, radiation. We can define the radiation basically as heat that is transmitted by means of electromagnetic waves. That is the concept. So some characteristics of this type of waves are that they do not require a medium to propagate. That they can even move in a vacuum, and also they travel at the speed of light since they only transport energy and not matter. But it must also be said that although it may not seem so, all bodies emit radiation. So regardless to their temperature, which means that even we as human beings emit electromagnetic radiation too. So let me try to illustrate better this idea. This mechanism generally works like this. So the energy carried by this wave is released when the body absorbs these waves. So for example, here we can have a campfire and a person. So according to what we were saying, both the campfire and the person emit radiation, right? So the difference is that the campfire, being much hotter, emits a greater amount of radiation. What happens in this case is that if a body absorbs more radiation that it emits, its temperature will increase. So in this case, the person is receiving a greater amount of radiation that it is emitting. So the temperature will increase, and that is why the campfire hits the person. That is how this works, and this is a good example to explain how the radiation is working. Mm, so the higher the temperature of the emitting body, the greatest the amount of radiation it will emit. That is the idea. Since it has been shown that the amount of radiation emitted is proportional to the temperature raised to the 4 pounded. This is a relationship well established for this kind of mechanism. So what this means is basically that a small increment in the temperature of a body means a significant increment in the amount of radiation that the body emits. For example, an anvil that is in a room temperature, let's see 20 degrees Celsius, will emit a certain amount of radiation. However, if we add heat to it and increase its temperature, for example, to 100 degrees, the amount of radiation that this anvil will emit will be greater. And same situation, it will increase 3 times more the temperature. So the amount of radiation will be greater. Mm, not all radiation is of the same type. That is something that we have to keep on mind. Since there is a characteristic of this mm, type of mechanism that is known as a wavelength. So this is the distance basically between the crest of an electromagnetic wave. And as we can deduce, it is directly related to the frequency of the wave. So mm, what we are saying with this is that if we have a shorter wavelength, we will have a higher frequency. While if we have a longer wavelength, we will have a lower frequency. And all of this is important since the wavelength is also related to the temperature of the object that emits this radiation. So in other words, the wavelength of the radiation emitted by an object depends on its temperature. There is a relation between these two elements. So the higher the temperature of the body, the shorter the wavelength of the radiation it emits. So this principle is used by current telescopes to observe the stars and the deep space. And this physics is determined by the the Wien's law that is expressed by this relationship here. So if we compare, following the previous example, if we compare the sun, which has an average temperature of about 6,000 degrees Kelvin with air, which has an average temperature of 288 degrees Kelvin, we will see that the sun emits a radiation with a shorter wavelength that the air can emit, basically. And it must also be said that the amount of energy transported also depends of the wavelength, since the shorter the wavelength, the greater the energy transported, and vice versa. So according to this, the sun emits more energetic radiation that the air can emit against because the air because the sun, sorry, has a shorter wavelength. So with this, we can see that the difference between the types of radiation, right, which we can analyze more easily by observing the electromagnetic spectrum, since depends on their wavelength, they can be classified in different groups. Mm, although this is a very interesting topic, I particularly like it a lot because I love astronomy. So today is not the main topic of discussion. So we will leave the idea in that point. We have different groups of waves. There is a dependence of the wavelet, and they are associated with the different types of radiation. But this is the mechanism that we have behind. So let's get down to the business. So all the theoretical framework above applies to the geothermal wells too. That is the idea, and that is why I try to establish this baseline of concepts. So if we think about the fact that we are producing or injecting hot fluids, all these heat transfer theory should be applicable to these problems. So what we see here is a road outline of what well-producing fluids from a reservoir can do. In a conventional situation, we know that the temperature at which these fluids enter into the well can be low, medium, or high, but certainly that temperature is much higher than the surface temperature. So we also know that there is a temperature gradient associated with the layers of the subsoil, and heat is transferred from the interior of the air to the crush. Uh, that is in this scenario, it is clear that there are temperature deltas everywhere, and that is the movement of fluids. That is basically what the movement of fluids is playing in an additional role to the temperature transfer. So this situation in general is indicating that we are going to have a heat transfer. So now let's see where the mechanisms that we already covered before applied into the system. So first, for example, we will have conduction in the formation, right? In the cement that fits the pipe, and in the same wall thickness of the pipes, called, let's say, pipe, tubing, or casing. We are going to have to force convection since the fluid is being producing. There is a pressure, a difference of pressure along the pipe, which will generate movement of that fluid, and consequently, we will have forced conversion in this area. Additionally, in the annulus, that is the basically space that we have between the tubing and this casing that we have placed here. There is also retained fluids. There maybe are not necessary motion. That will depend on the type of completion that is done. But in this diagram, we have a plug in this lower section of the well. So we could say that these fluids that we have here are not being affected by movement. However, they can gain or lose heat. And as we said before, this temperature, this difference in temperature impact the density, generating movement and heat transfer. So here we will have a case of natural convection. Finally, we could have radiation between the walls of the pipes, since, as we explained before, anybody that is at a given temperature emits radiation. So all of these mechanisms are grouped together, and the task now is to put all of this into a mathematical model that allow us to make estimations of the temperature condition of this fluid inside the production pipe. Um, this apply not only to the production, this can apply to for injection. So in any case, the analysis is applicable because basically this is the thermal model where we are trying to look for. So now let's see how we are going to model the temperature in the well. Mm, so the first thing that we are going to do is take a diagram of a well, and we are going to discretize into small segments, as we can see here. Mm, this is going to help us to perform a localized analysis. Then what we are going to do is extend that analysis that we are doing in a small control volume to the entire section of the well. Now, in this control volume, we will have a mass flow inlet and outlet, since we are producing a fluid from the reservoir. And in turn, there will be a temperature, a difference of temperature between this point and this point. So the fluid within this control volume could have an average temperature that come from an average from the temperature in and temperature out. And if we can put it that way, and this will contrast with the temperature of the surroundings or the formation that we have around of a well, also generating a delta of temperature in this direction. So this is the direction that we are interested uh, in, because what we want to see is how much heat the fluid that we are transporting could lose or gain through the interaction with the environment that is around it. So establish the conservation equation in terms of the energy for this control volume. We will have the heat, the mechanical work equal to the flow rate, and the difference between the energy that comes in and comes out of the control volume. This energy that we have here in and out can be split usually in three types of energy. So we're talking about internal energy that is basically defined by enthalpy. That is the energy that comes with the fluid that we are transporting. The potential energy that is related to the depth and the location of the point that we are analyzing, and the kinetic energy that are related with the velocity of that fluid. So there is no work in this system like the one what we know from thermodynamics, for example, the piston type or any external work acting on this control volume. So we can remove the term from the equation. And in that way, we can go from this step to this equation that we have here. So the first is basically an expansion for the point out and the point in. And we have here the expression of the internal energy in terms of the enthalpy, the potential energy in terms of the true vertical depth, and the kinetic energy expressed by the velocity. So now we can go the deltas in terms of enthalpy, deltas in terms of potential energy, and the difference in the kinetic energy for each point. So now with this equation in mind, we can take the differentials through zero. And in that way, we can transform this differential equation, this delta equation, sorry, in a differential equation. So for the case of incompressible liquids, well, incompressible fluids, yeah, the kinetic energy becomes to zero. And this is because basically in fluid dynamics, the kinetic energy term in the Bernoulli equation is zero when the pressure at 2 points is the same. The potential energy term goes away, basically. So this is because the density cancels out and leaving the equation with zero on the right hand side. In that way, this expression is reduced to this, And now we can reaccommodate the terms and expand again, opening the enthalpy term and adding the potential term of energy. So now with this equation, that is exactly the same that we have here. So let's go to explain what is happening with the enthalpies. So let's analyze the enthalpy at the point 1 that is in the inlet. So this enthalpy is basically defined for the mixing of all the fluids that can comes into the well. This is a general expression or a general term that can depends of the fraction of gas, oil, and water that we can get into the tubing, right? So it's a mixture. So this fraction for each phase is defined by the amount of each phase and divided by the amount of total mass that we have into the stream. But if we have a water dominated system, like usually happens in the geothermal wells, we can basically remove the term associated to the gas and the oil, but just if we have a liquid, right? Water dominated system as a liquid. If we have steam in the stream, we will need to keep with this part of the equation. And basically that will represent the steam portion. And we will need to include the quality of the steam concept into the model. So at this point, the balance between nodes and unknowns let us to identify that we have one equation, two unknowns. Each one, the enthalpy at the point 1 will depends basically of the PWF, that is the pressure at this point of the well, and the temperature of the at this point, or the temperature of the reservoir. But in terms of the flow rate, that is this term, the M term that we have here, that will represent the reservoir model. We are going to talk about that term in the further topics. And we are going to suppose that we know the distribution of the pressure along the well. That is something that we are not going to solve in this moment. Usually in the commercial software, what is happening in the background is that temperature and pressure are solving in parallel. But in this case, we are not describe what is happening with this. So we are assuming, we are going to assume that we know the distribution along the well. So now, this flow, this heat that we have here depends of these two temperatures that we have, the temperature, the average temperature of the fluid and the temperature outside. And basically, if we can calculate in some way this heat, we can estimate now what is the value of the enthalpy at this point, in point 2. This is an equation that we can keep here in mind. And now, if we assuming already that we know the pressure here, and assuming a temperature in this point, we can go for the value of the enthalpy at this point. So with these two components, we can make a comparison. And if all of them are, if the enthalpy calculated here and the enthalpy estimated here are equal, basically we can assume that the temperature that we assume is correct, right? So we're talking about, we have here is an iterative process. If we want to avoid that iterative process, what we can do is basically to use this expression that we have here and express this delta P as a function of the heat capacity of the fluid. In terms of the liquids, We can express that delta enthalpy as a fluid capacity times multiplied by the delta of the gas of pressure and temperature. And this probably can imply also an iterative process. Now, let's see that we have a water-dominated system and a liquid phase. So keep in mind all the simplification that we are developing, because that will condition the model that we are going to get at the end. So now we have an expression here that just have one no, that is the heat, this term. We said in the slide before that we can estimate this heat in some way. Let's see how can we do that. The expression that we can use to estimate this heat, the heat that we are basically transferring between these 2 points, are based on 2 terms. U, a geometrical parameter, and a delta of temperatures between these 2 points. But that heat basically is composed by all the mechanisms that we talked before. Basically, we are talking about this heat is a combination between conduction, forced convection, free convection, and radiation. So let's try to open the expression a little bit better. So the first term that we can break down here is the area. What we have is a simple cylinder that is the physical shape of our control volume, and its dimensions are associated with the dimension of the pipe, basically. However, it is important to remark and to know that we don't just have a tube, a single tube here. So if you remember the schematic of the diagram that I showed you a couple of slides before, the diagram, the schematic of a well has a lot of components. You know, we have a tubing, we have a casing, we have the casing is cemented, and this whole arrangement is bound to the rock through cement as well. So actually, the heat will cross all of these components, all of these layers, from the axial axis to the formation or the rock. So this will lead us to define between which zones we will have conduction, we will have um, forced convection, natural convection, or radiation. And in the case of conduction, we will speak of a thermal conductivity, which in many of these cases is more an average conductivity. In the case of forced convection, this coefficient, this convective coefficient, will have a strong dependence of a mixture between different physical numbers, a dimensionless number, the Reynolds number, the Prandtl number for the case of natural convection. For the case of forced convection, Prandtl number and Grashof number in the case of natural convection. And we can identify here is that in the case of convection, all of these coefficients themselves depend strongly on temperature. So here we have another source of iteration process into the calculations that probably we will need to do in terms of a more complex system. So finally, if we consider the radiation, this coefficient will also have a dependence on the Stefan Boltzmann constant and the emissivity. So all of these dynamics and all of these coefficients will be encapsulated in a unique coefficient that we know as a overall heat transfer coefficient. That also depends of a geometrical parameter that usually is the distance, the radius between the axial point until the zone that we need to analyze. So let's back in this equation. And for the purpose of this analysis, we are going to focus in conduction and convection. The thermal conduction and convection are the dominant mechanisms in the case of a liquid filling in the annulus. The thermal radiation can be ignored. The radiation is considered to occur only when we have an annulus that is filled with gas or is vacuum. This is not the case that we are analyzing in this moment. So that is why we are focused just on conduction and convection. So this is the original equation that we have that express the energy in terms of the section, the area, sectional, the overall heat transfer coefficient, and the delta of temperatures. Here we have the models for conduction and convection. So now what we need to do is to identify clearly each zone in our model. This is an example, and I want to be clear on that. So all of this analysis will depend of what will be the final arrangement or the completion of the well that we are trying to analyze. But this is an example that illustrates how we are going to estimate this unique overall heat transfer coefficient. So here we have the temperature of the fluid, this point, the temperature in the inner section of the tubing, outside of the tubing, inside the casing, outside the casing, inside um, of the internal casing between these two layers of cement, uh, outside of the internal casing in this area. And this is the temperature of the wellbore that for this purpose, we're going to assume that is a good representative of the temperature of the reservoir. We know that this is not uh, totally true because there is a gradient in the rock too. Once we are going more far away from the axial axis. But for this proposal, we are going to assume that this is a good estimation of this temperature here. So now what we have is uh, a contribution of every single mechanism of heat into the total heat that we are transferring here across these layers. So keeping this in mind, what we can do is, okay, we have here conduction in the tubing, the expression that we can, convection, sorry, in the tubing, force it. This is the expression that we can use. And this comes, remember, this equation that we have. This is the general model. And this is the coefficient for convection, in this case, force. So if we have now conduction in the tubing, in the wall of the tubing, this is the expression that we have here. Yeah, look at is different. There is the dependency of the conductivity in the tubing, and there is this relationship, geometrical relationship between the external radius and the internal radius of the tubing. That basically that form of the equation comes from this part. So now we add the convection in the annulus, conduction in the casing, conduction on the first layer of cement, conduction in the internal casing, the casing that we have between each layer of cement for this example. Yeah. And remember that we have a final layer of cement that is contained here. So all of these components add elements into the equation. And that is why the final expression looks like we are seeing here. With this in mind, what we are going to do is basically to rearrange by applying some manipulation of the terms and a little bit of algebra. So now what we are in this case, the only thing that I am doing is to clear the temperature, the delta of temperature, so we can work better and identify the elements of the main equation. That is what I am trying to pursue with this development. So here we simply applied a little bit of algebra, as I say, and clearing the temperature, the difference of temperature between the fluid and the wellbore, we get this expression. So this expression already basically has a delta of temperature between the fluid, which will be its average temperature, right? Uh, and the well phase, the average temperature of the fluid and the temperature in the wellbore, basically. We already know as I say before, that this is not true, but this is the best approach that we can consider in this development so far, just for simplification. So we can assume that this assumption is valid. Next, now to accommodate the terms a little bit better, we're going to use as a reference value to simplify all the expression the inner radius of the well. So we're talking about this area or this part of the system. So in this case, we will take the internal radius of the tubing, the factor, and factoring the expression. Then we have this expression that we have here, right? So this expression in red is representing the combining effect of all the coefficients of all the heat transfer mechanisms that are present into the well. So now this expression is, as I say before, is just an example about how the well can be configured. But this expression in red is basically the overall heat transfer coefficient, and that can be expressed in watts per meter square per Kelvin, or BTU per feet square hour per Fahrenheit. So, mm, and as I say before, this is just an example. And what I want to illustrate here is why, in many cases, we need a simplification of all of the system by using a unique simple equation. Just because the system can change and the system can be more complex. And notice, for example, that here we have not represent an insulated coating, which is something that is associated with the completion of a geothermal well. However, I think that in this example, with this short mathematical development, we can illustrate the idea about what is behind of that variable, called the overall heat transfer coefficient. So now with this in mind, the heat transfer coefficient, the overall heat transfer coefficient looks like this. And what we can say in terms of the physics related to this variable is that if this coefficient is low, the heat losses are low, basically. But if we have a higher value of this coefficient, the heat loss will be higher too. So if we understand this, we can go for a general modeling. We can model the temperature profile along the well in a very global value without getting to the calculations related to each mechanism that we have present into the well. Sometimes we don't have too much information related to that, or sometimes we are not decided already what will be the completion scheme that we are going to apply. But in terms of make sensitivities, to know this approach can be really useful to manage an approximation of the temperature profile in the well. In addition, what we can see here is that as you see in the mathematical expression, there is a strong dependence of properties related to the rock, related to the steel, and related to the cement. So we can find databases, thermal properties databases related to every single situation in particular that compose the system that we want to analyze. So now we have back to our initial analysis. We have two equations. So two ways of expressing the same heat. And now we are going to combine them to generate the mathematical model that describe the temperature of the fluid along the well. So this is the two main mathematical expression that we have been analyzing so far. So we express some terms explicitly, right? And we are not going to affect the overall heat transfer coefficient. We are just going to move variables from one side to another side to create the differential equation. And here we have basically the form of the equation that we have to solve. To propose a solution for this equation, there are many options that exist so far, but the Ramey equation is one of the most well-known and widely used in terms to offer an analytical solution to this differential equation that we have here. We can say, and according to the literacy and industrial studies, this equation has reported satisfactory results. So this equation is working well in terms of the match fit results. So let's take a look on which what is the meaning of each component into this equation. So the first term that we have here is the TF, that is the injection buttonhole temperature. Remember that this development was made around 1962. So Ramey was developing this equation thinking in an injection well, mostly. Yeah, so that is why this term appears explicitly into the solution. This expression of this, A zeta plus B, is the linear geothermal gradient. This zeta that we have is the true vertical depth. And this is an equation because this is an equation that can let you know the temperature of at each depth that you need along the well. TO is the injection temperature at surface, and LR is the relaxation coefficient. So we are going to see what that coefficient implies. So first, we have to remark that TO, this term that we have here, usually is the unknown that we have in the typical studies that we are doing, because in the normal scenario, what we have is a well that is producing at hot fluid that come from the reservoir. So what we want to know is what is the temperature at the well head. So this is usually the variable that we are pursuing. And in contrast, this temperature that we have here is assuming as the temperature that we can estimate for the reservoir. Normally, by using the calculations that come from a geothermal gradient when we have a really strong lack of information. So now going deep into the relaxation coefficient, that is this variable that we have here present in these areas of the equation. Basically, this is primarily a function of the overall heat transfer coefficient. That is why we need to know on which range we can move that value, what can be the value associated to the situation that we have. If we don't know, we can go for the calculation, but you now know what is the expression behind this value and the amount of information that we need to know and define in terms to estimate that value. So we have two, the CP, that is the specific heat of the fluid. This is the mass flow rate. We have the thermal conductivity of the formation. And this term here is a dimensionless temperature function that was expressed in a logarithmic expression based on the injection time. As I said before, that was the study that was developed by Ramey in 1962. So he was thinking in that scenario. But that can work too if we are trying to analyze in transient mode or system. Usually what we can do as a first clue is just to analyze the system in a steady state. So that basically imply that we are making the calculation like in a picture. It's not something that cover the transient behavior. Mm, However, at this point, seems like we have already solved the problem, by using this expression that we have here. But there is a term that has gone in some way unnoticed throughout all of this development. So is what can I say is a small diagram that is really decisive when we are trying to estimate the geothermal potential of a resource. And that term is precisely the mass flow. So many academic exercise, it is taken for a granted, is assumed as known, but in the reality, the reality is that it is another part of the problem that we have to estimate. So we are talking about basically the flow rate of the well and what can be the potential to produce, let's see, hot water or a steam or a mixing of these fluids. So mm, the reason because this is important is because this term is a function between the potential of the reservoir and and uh, and also depends of the completion that we are applying. I mean, it's not the same if we use, for example, a 5 inches pipe or a 7 inches pipe. It's not the same if we have a well flowing naturally or if we are applying an artificial lift system. So all of that elements are conditioning this component of the equation. So to get into the way in which we can calculate this can be quite extensive, but I will try to provide a glimpse about how can we avoid in a general way this value and how can we estimate in some way the potential of the flow. So for the reservoir model, we can apply a very general approximation. And this approximation comes from Darcy laws. Basically, with this model, what we are trying to put in together is the interaction of the parameters that describe the reservoir. We are talking about porosity, permeability, fluid properties, rock properties, saturation of fluids. Mm, in general terms, what we are trying to establish is in some way what can be the range of flow rates that we can get from the reservoir. So the typical parameters for use this Darcy law are the reservoir pressure, the reservoir temperature, water cut, the total GOR, permeability, thickness, drainage areas, and wellbore radius, right? But again, in some cases, most of these parameters, if we don't have enough data, we need to assume it, yeah, in some way by using the best estimation possible. So this is an example of how these reservoir models are available in commercial software. And you can see a lot of models. Darcy is just one of the models that we have available to estimate what can be the flow rate that comes from the reservoir. But the use of many of them that can be or that can imply, to know more or less parameters, or that can imply a situation, particular situation into the system, like considering, for example, fractures or the effect of an active aquifer connected to the well, for example. Here we have an, 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 a description about what is happening with the fluids when usually we are talking about the oil and gas system. You can see here the expression of this term, that is the permeability to the oil, the viscosity of the oil, and the volumetric factor of oil, right? But this is act like a correction of the Darcy law, because the Darcy law was developed for water. So in oil and gas system, we introduced this physical term that describe or let us describe what is happening once we have a liberation of light hydrocarbons into the fluids, and what is happening from an amount of volume that come from the reservoir to surface. So normally, yeah, the effect of the reservoir pressure um, generate a profile in terms of time and flow rates like we can see here, right? There is a kind of arc, let's see, in that way. But basically, there is a physics behind. So because under the bubble pressure, we are going to have the effect of that fluid liberation that we have into the reservoir. To calculate the flow rates, because what we are estimating here along this line is the flow rates. To calculate that flow rates, we use the Darcy law, or we use the Darcy model when the pressure that we are analyzing are up to the bubble pressure. In the bubble pressure, we use the stabilized test data point, a QMPWF, to define this critical point, and down to this, we use a different model, which is the Vogel's equation model. But the situation changes when we are not talking about oil and gas systems, basically. When we have, for example, following the same approximation that we defined before, if we talk just about hot water, so if we are quite sure that at this pressure and this temperature, what we have in terms of the thermodynamic system is just a liquid, and same thing at the wellhead, and there is no change of phase along the well while I am producing the hot water until the top. So basically, the model that we can use is the Darcy model, because we are not going to have this bubble pressure here, and this line can be extended. Yep. In gas phase, the behavior is different. Yeah, because we are talking about a compressible fluid. That is why we have this trend here, because the compressibility and the liberation of fluids that we have at the reservoir condition. So this is an example of the incidence of the reservoir properties in the flow rate. We can see this straight line at the different reservoir properties. For example, this line that we have here is in a reservoir with 10 millidarcies, a porosity of 18%, and a thickness of 16 meters. So now if we improve the permeability and the thickness, we can move this line until this position. And again, if we have an improvement of the permeability, for example, from 10 millidarcies until 120 millidarcies, we will have this condition that describe basically the flow that comes from the reservoir, right? So what this situation is telling us is that we need to know what are the properties associated to the reservoir in order to know what can be the potential of that reservoir to produce the fluids that we need. It's not just a matter related to the temperature or how much thermal losses we have along the well. So we need a potential here connected to our system, because basically that is the system that we provide us along the time, all the fluid that we are going to produce, which will be basically the source of the energy that we are taking at surface. So this line that we have here is basically reproducing the condition, but in the well, right? So when these two lines cross each other, we have a real flow rate, or what can be interpreted like the real flow rate that we are going to have here. So look, in terms of this combination, we can see perfectly that in spite of we have good properties here, if we have a completion that in the well that is not provide us with a good flow rate, probably we are not going to get too much from this potential. So what we use usually is to move this point to this zone or this zone by using, for example, an artificial lift system in order to help the fluid to reach the wellhead, right? So usually in many of the studies, the typical flow rate that we are looking for is around 50 liters per second. That it can be considered a good flow rate for a let's see an average geothermal resource. So summarizing in terms of the simplified model, yeah, most of the development that we saw here is conditioning to a steady state, but uh, if we reduce the analysis, or we want to do the analysis for a first step in order to look for more information related to our geothermal assessment, we look for or the equation works really well if we have a water dominated system, talking about single phase liquid. We're talking about incompressible fluids. The overall heat transfer coefficient should be assumed in most of the cases, or can be assumed in order to get a rough approximation. No phase change along the tubing. This is quite important, because if we have a liquid at the bottom, but we have steam at the top plus liquid, so that implies that we will have a phase change along the well, and the model that we present is not covering that situation. And we can cover the reservoir model by using the Darcy model in all this extension. We don't need to go for any model that consider any other fluid dissolved into the fluids that we have in the reservoir. So finally, to go for an overview of the geothermal reservoirs modeling, we're going to talk about, well, what we present so far is a simplification of about can we work with all of these elements at the well level. And this can work perfectly if we have a situation where there is a lack of information or we don't understand clearly what is happening with the resource. So it's not good go for the most complicated approach at the first step, because basically what we need to understand if we have the capability to cover the energy demand that we're trying to cover. And that is why I will present this last part of the presentation. So in terms of the geologic perspective on the geothermal plate system, and probably you covered this topic in some session, but I think that what we need to add in terms of this topic is that in the definition of the hydrocarbon plate systems, we found basically that they are clearly defined by the source rock, the reservoir, and the trap. But in terms of a geothermal place, are lacking, such as a clear set of geological features. Instead, the geothermal place systems appear in diverse geological environments, and theoretically, you have geothermal plays and potential along the world, uh, everywhere. So for geothermal resource utilization, there is basically two factors that are quite important. The how much heat is stored and drillable depth, and if this and also if this heat is producible, yeah, and which economical rate for a specific project. So that is why usually in this kind of analysis, the economical analysis is quite important to determine if the project can be go or not. So in addition, we can remark that the characteristic of the individual geothermal system are a function of the site-specific variables. So we're talking about the nature and the depth of the heat source, the dominant heat transfer mechanism, as we saw previously, the permeability and porosity distribution, as we saw by applying the reservoir model, fluid rock chemistry, that is a component that is not taken into account into the models that we saw previously. Yeah, the fluid recharge rate source, and identify the plate type that is focused in the exploration strategy. So in terms of the type of geothermal reservoirs, we can categorize all of them basically in six, sorry, groups. So the magmatic or magma or molten rock, yeah, the magmatic reservoirs. Basically, in this kind of geothermal reservoirs, the heated water can be up to 1,000 degrees Celsius and is saturated with corrosive chemicals. That is why we mentioned before that the chemical component is quite important. So the heat from the water can be converted into usable energy because the energy associated is quite high. As a benefit, we can say that basically the magma geothermal system can provide renewable energy. The water is usually at supercritical conditions, and we can generate, according to the studies, more than 10 times more power than in a conventional source. The problem with this kind of reservoirs is that producing energy from deep geothermal source, uh, such as in this case a magma, can be challenging. However, there are methods that let you address this challenge. For example, um, using or applying, for example, the advanced thermodynamic techniques applied to the fluids in order to stabilize the well's walls. That is the most critical problem in this kind of reservoir. In terms of the plutonic reservoirs, uh, we can say that basically a plutonic geothermal system is a type of system uh, that is characterized by deep location too, but is close to the magmatic phenomena. It's not precisely in the magmatic zone, it's close to that. So that implies that basically these kind of reservoirs are founded along continent or continent convergence or transform margins where there is a recent magmatism. Mm, in terms of the extensional domain geothermal reservoirs, um, what we can say is that this is not a is non-magmatic geothermal plate. It's more like a combination of orogenic and sedimentary basin with an asymmetric geology. So in this in these systems, there is a high level of groundwater circulation. That is one of the characteristics. There is basically a foul control because the system can be either foul controlled or fall leak controlled. So this can give you a glimpse about how complicated can be model these kind of systems. There is a thermal fluid mixing, and there are strong candidates for a numerical simulation. In terms of intracratonic basins, what we are describing here is basically a kind of sedimentary basin that forms in the middle of a stable continental plate. So here, what we have is a subcircular shaped a structure that is filled by sedimentary rocks. Is more that that sedimentary environment. In the term of orogenic belts, yeah, basically what we have is a lot of compression, magmatism, topographic rise, erosion. So there is a strong geomechanical component associated to the modeling of these kind of reservoirs. And finally, talking about the crystalline rocks, what we have is a variety, or this comprehends a variety of systems, but they are more arrow to the enthalpy. The enthalpy, to define in terms of low, medium, and high enthalpy, is the key parameter to describe this kind of geothermal reservoirs. So here you have a table that describes how can we estimate or classify a low enthalpy, moderate enthalpy, and high enthalpy system. And you can use this for your own reference in order to apply it into the further exercise that you are going to develop. And what we can see here is how a simplified geomodel, as a case of example, can looks like. So here, what we are trying to do is basically to model an area of 3,000 meters per 5,000 meters with a vertical extension of 500.5 meters. So we are using a cell size of 75 cells, 125 cells, and 25 cells, meters per cell. And basically, what we need to to have is to make a model which let us take into account the pressure, temperature, and include the geological properties like porosity, permeability, and all the information that is available in the region. So we are have a supercritical fluid in one zone, and the other zone is not in that condition. And basically here we can see the temperature profile that we got from the simulations. So the initial condition basically is determining the coexistence of superheat water and supercritical water in this kind of model. And what we are getting as an outcome of this model is the thermal power output. This is quite important because in terms of the system cycle, what we have is a connection between a reservoir and the production wells with the surface system that basically is composed by the geothermal plant and finally the grid connection. So what we covering today in a general way was okay, what is happening with the geothermal reservoir and what is happening with the production wells with a simplified model. Yeah, but this model or this part of the system is connected to the geothermal plant, and that plant is providing basically inputs to other part of the system that are linked to. So in this diagram, you can see how usually this looks like. So we're talking here that we have the reservoir, we have our analysis here, and after applying our model, we can estimate what can be the temperature of the well top, right? And with this temperature, we can establish what is the amount of energy that we can get from the fluid at this point. This is not the total energy that we have available. If we can get some percentage of that energy, we need to get that energy by create a drop of temperature. And this temperature that we have here, we will define as the temperature of return to the reservoir. So this delta T is creating basically an amount of energy, but that amount of energy is considered by a thermal power output, right? That is the amount of energy that we are going to put into the geothermal plant. But again, this amount of energy is not the final total energy that we are going to use in terms to the electricity system, because this energy that we have here is affected by the efficiency of the plant. So look how much energy we can lose into the process. So it's not a thing just to evaluate this part of the system. You will need also to get into consideration what can be the temperature of return, how much thermal power output you are going to put into the geothermal plant, and what can be the efficiency that you are going to apply into the geothermal plant to get the final electricity thermal output that basically is the fraction of this thermal energy by using the efficiency of the uh, geothermal plant, which limit of efficiency basically is the Carnot cycle. So with these ideas, I conclude the presentation for today. I don't know if Yamal has any other idea to add in terms of the geothermal systems and the way in which we are usually applying the simulation or reservoir simulation to these systems.
Uh, Elkin, thank you for your presentation. I think so. The idea that we want to present in here has been well covered for you. And if not, nothing to add from my side. Appreciate it.
Thank you. Thank you very much, Yamal. Thank you very much, Elkin, for such a detailed presentation, kind of going through the whole process of, the heat transfer types and generally walking into the equation and what that would mean when you're looking at the wellbore and the reservoir itself. I do want to mention that there was a question in the chat box from Thomas that said, considering a flow rate of 60 to 80 liters per second, which is about 38,000 barrels per day, does conduction, convection, or radiation play any reasonable role compared with reservoir heat?
Well, let me. So the question is looking for what kind of system we are looking for, because basically what we can say at this point is, okay, so if we are considering a rate between 60 and 80 liters per second, so what we have is a range of rates that usually are into the range of viable flow rates to get a good value, or a good value of wellhead temperature. But we need to get into the considerations of how big can be the overall heat transfer coefficient, because that will determine by the end how much thermal loss we are going to have, right? So yeah.
Okay. I mean, that kind of ties into a thought here. One of the important things during the hackathon challenge is understanding what the log inputs are. So basically creating an understanding of the density of the rock, so the type of rock, and then going into what those thermal conductivities of these materials would be, and then is the system permeable enough to get the flow through, and what that would mean for the overall output on surface, thermal to electrical, or would you need to stimulate, right? But part of this challenge is it doesn't account for the opportunity to actually create tensile fractures because of its inapplicability right now in Europe, let's say. But I think it's an important thing to keep in mind. We do have one more question, and that's coming from Diana Hernandez. And she says, thank you for the excellent presentation. I have just a question. The workflow that you presented is used for feasibility studies and to get a first understanding of the geothermal potential. Then based on this insight, we can feed the reservoir simulation for developing the plan, correct?
Yes, in a first, I will say that in a first step, yeah. What is important to understand is that in the approach that we present today, we are trying to be practical in some way, and that estimations just work to understand basically the potential of the geothermal resource. Yeah, but in terms of the reservoir simulation, we are going to need more elements. We are going to need more information to go for a proper model. Yeah.
Diana, and also, sorry for one second, Gabriel, just to add to your question, Diana. Essentially, what we wanted, I mean, sometimes, all this kind of approach is time consuming, right? And everything is depend to a budget that is available and what exactly you want to understand from the answer you are looking for. So first approach, we try to go with, a more, let's call it like that, steady state modeling, right? That we can get information at the wellhead. And as you mentioned later on, we can use that information into dynamic simulation. Remember that dynamic simulation, as I mentioned, will cover a more extensive information, and it will be more, robust and also time consuming. Again, it depends what answer you're looking for. Sometimes operationally and companies that try to develop geothermal field, they are more inclined to just capture information and try to have a high level approach that they can later on measure at the field level when they do some well test. Again, it depends what exactly you are trying to figure out in here. And dynamic simulation as well sometimes is useful to understand, like when you having a production and injection process, you want to understand when the cold front will reach those producers, because that will affect the capacity you will have to generate energy at the surface. So it's a lot of concepts involved in dynamic simulation as well.
Absolutely. And one thing to add to that, Yamal, I think is the granularity of the process that you're doing, right? It's a workflow, just like it's in oil and gas, as you're gathering real data from the field. you're feeding the simulator and then you keep rerunning the model to try to understand how things are changing. And a lot of that is dependent on the type of data that you have available and the quality of data that you're working with, correct?
Okay.
Thank you very much. We got a couple of thank yous in the chat box. Once more, I would like to remind everyone that we're going to be sending the recording and the slides on the Discord channel, so you can always go back to the equations, kind of sit down and go through them yourselves. You're probably going to have to code some of those in Python and just understand the fundamentals of it and how you're going to apply it through your process. So I think this is super important. I would like to thank you, Elkin, Yamal, for such a great session and for your availability. If there will be questions during the hackathon that could possibly need some answers, we'll reach out to you. And then just wanted to thank you guys once again, the audience, and be prepared for next week's last two sessions. One is going to be on the field development for geothermal projects, and the other one will have Davis from Baker Hughes and Gaffney Klein talking about project economics, right? Once you set up everything, how is this going to translate into cost? And will it make sense economically, to supply a town of 50,000 people with power, and how is that driven? Because that tends to be one of the biggest driving factors in terms of geothermal development. So looking forward to it. We've had a lot of great teams signing up. We're working on setting teams up, just kind of doing the logistics in the background, and the hackathon will kick off soon. So it's going to be an exciting time. Thank you everyone once again.